Morning, everyone. Um, any question for last week lectures and tutorial? I got an email from 黄静豪 is here. Is 黄静豪 here? Oh, 黄静豪. Okay. So I just answered it from the class. Okay. So you asked about this question 2.6.4c. And then this, I think I got 3 email on this question. I think I changed it. Can you check whether the online version is already changed? Yeah. Yeah, it's wrong. Yeah. Yeah, I already changed it. And I also found that, yeah, okay. So first of all, it's this about this column here. So to find this column, you use the first row on the first matrix and then multiply with the second row, first column of the second matrix. So it's 0 times 4 plus -1 times -2, which is 2. Okay. I think the file getting larger, so it's hard to download. So maybe I will split the file again next time when I upload the lecture. Any other question on the tutorials? That's it. It's not there's some notice I want to make. Because this law here, there's no name for the law uh, in the textbook, right? So I invent a name, maybe call it the implication disjunction law, or maybe you call it a conditional disjunction equivalence. Okay. First is about relating the conditional statement with the uh, compound proposition uh, that involve disjunction. Okay. And, and then one mistake that people usually make is some of you tends to put the intersection. This one is that intersection. And then this one is the um, conjunction of proposition. So besides set, what you put is two sets, right? So these are sets. But beside the conjunction, you should put two propositions. Okay. So don't put set beside your conjunction. This one is wrong. And don't put proposition beside the intersection. What does it mean by two proposition intersecting? Okay, so one is the rounded one, one is the sharp. Yeah. Don't confuse. Similarly for the union. For the union also. Union. Okay. Okay. So I think of a way for you to ask questions. So if you really don't want to ask on the spot, or you shy, or you maybe get stuck, you can email me 5 minutes before the lecture or during the break. And then when the class starts, then I'll bring up the question in front of the class so that everyone can learn together. So question time, make sure you make full use because this is the time that you can talk to me. Because sometimes I will go too fast, but I don't know whether you know it or not. I mean, whether you learn it or not. Because maybe something for me is trivial, but it's not trivial for you because you see it from the other view, which I haven't seen before. Okay, so I offer the time for you to ask questions so that we can talk to each other. Make sure you uh, make full use. Okay. Any other question? No? No, then we will go to today's lecture. Okay, today we will start a new topic, which is Week 3 and Chapter 4 in your textbook is the number theory and cryptography. Of course, this subject is large by itself. It can grow into a 4-semester topic. So you can imagine that we have skipped some. We only can cover a little bit of this subject. This week we will focus on number theory, and then next week we will do cryptography. Yeah, this crypto is the same as the cryptocurrency. So cryptocurrency use cryptography to encrypt the money. Okay. Okay. The first part we do is the modular arithmetic. The goal of this part is to write down the goal first. So the goal of this part is to study a finite set of number. Okay. So for example, a finite set of number, I just give it a name first. Remember the clock number that we gave last time? One, two. Okay, and then learn how to add, add and multiply inside this number. Okay. So for example, if you learn that the clock, if you have 12 to 1 plus 1, it's actually okay, let me do it again. So if you have, okay, like what is 1 hour after 12 p.m.? So 12 plus 1 is what? You go back to what? 1 a.m. Okay, yeah. Okay. So how you like add inside this set of number? Okay. But the way we're looking at it in this class, we'll be using the divisibility. So what does it mean by that? So because, for example, this is actually 13, right? So why 13 is equal to 1 in this case? Okay. Because if you take 13 minus 1 and then divide by 12 is 1. So it's another, is in other words, this is an integer. Okay. So the difference is divisible by 2. Okay. But we will go deep into it now. So to talk about divisibility, so we need to say what's the definition of divisibility. So take two numbers, two integers in particular. So suppose A is not 0. Okay. And we will say that A divides B. Okay. If there exists another number, C, which is an integer such that B equals to AC. Or if you do the normal division, you'll get A over B is an integer. Okay. And we will write A divides B in this case. And if A doesn't divide B, we write A doesn't divide. Okay. Slash the straight line. Okay. So when B divides AC, so when B divides AC, sorry, A divide B, we have B equals to AC, right? Then B is a multiple of A. And A is called a factor or divisor of B. Okay. So it's okay that if you don't follow this definition, but you have to follow what's the example is. Use the example to learn the definition. Okay. So the example is consider 2 divides 6. Okay. So what does it mean by 2 divides 6? It's because 6 I can write as 2 times 2. Yes. So 2 over 3 is, sorry, 6 over 2 is 3, which is an integer. Okay. So see, when I verify this definition here, I have to check the condition given here. Okay. So that's mean to, for example, this definition here, since 2 divides 6, we got 6 is a multiple of A. Okay. And then 2 is a, sorry, multiple of 2, and then this is a factor of 6. Okay, is it okay? Following. So, for example, second example, non-example. So 2 doesn't divide 7. Why? Because if you take 7 divided by 2, you get 7 divided by 2, 3.5, which is not a integer. Okay. 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 And next. Okay, next, take 3 integers. We want to see take 3 integers. Okay. First of all, take 3 integers. A, B, C. Okay. Such that one of them is non-zero. Then if A divides B and A divides C, then A will divide the sum of them. Okay. If A divide B, then A also divide a multiple of them. Okay. Also, if A divide B and B divide C, then A divide C. Okay. So let's see why is it true for one of them. So why is it A divide B, A divide C, A will divide sum of them? Okay, let's try it. Suppose A divide B and A divide C. Okay. So what we want to show is A will divide B plus C. So what does it mean to be A divide B? So we recall the definition. A divide B means B equals to A times C. So maybe we call it another name here because we have C in the assumption. So let's take M. Okay. There's some integer. Okay, some integer multiply A equals to B. And also we have C equals to A times maybe another integer. Okay. By assumption, by definition of divisibility. Okay. So what do we want to show? Okay. Let's see what's our goal. So A divide B plus C, meaning B plus C is equal to A times some integer. Okay. So what we have is we can combine the A plus B plus C we get AM plus AN, which is equal to A times M plus N. Okay. So M plus N is in Z. So that means A divide B plus C. Since M plus N is an integer. Okay. Still flowing. Okay. Okay. So okay. So uh, so maybe uh, try do 2 and 3 using the similar method. Okay. Okay. Let me copy this. Do you want me to try one more or we go to the next part? Huh? One more. You want two or three? Two. Okay, let's do two then. Okay, let's do two before we go to the next one. So two. Okay, so two, what do you have? Suppose that A divide B, right? So I want to show what A divides BC for all C in Z, right? So by assumption, you just use the definition you have. B is equal to what? A times some integer, right? Okay. So how about what does the goal mean? So you need to like sometimes you need to go forward a bit and then go backward a bit and then go forward a bit and go backward a bit. Then you can link the two together. Okay. I mean going backward, why? Because you want to understand your goal. Okay. So what is A divided BC means? So BC equals to A times some integer, right? Okay, so you need to find the H. Remember in the proposition logic, whenever you want to prove the existential quantifier, you need to find the H. Okay. So let's make use of what we have here. This one is what we got. This one is what we need to find. So, so, yeah, so I left out there is this. Okay, so to be precise, right? To be precise, I need to say for every C first. So for every C, there's this equation. Okay, to be precise. Okay, so we need to show for every C. So maybe take one C first. So take a C, arbitrary C. Take any C. We can multiply C on both sides, right? So BC equals to AMC. Okay. But notice that A times MC. MC is an integer. Right? So we have written as in the form of BC times A. BC equals to A times some integer. Okay. So hence A divide BC since MC is in Z. Okay. Yeah. So you can do the same for the third one. Write out what is the definition of this, and then write out what is the definition of this, and then write out what do you want to show, and then see if you can combine the two to show the goal. Okay. Yeah. Okay. It's again. In this case, maybe I want to disprove them because if we have time, maybe we'll come back to this proof. So if A, B, and C, okay. So this is a more powerful theorem here. So I take A, B, C in Z such that A is not zero. One of them have to be non-zero because zero cannot divide any number. So A divides B and A divides C. Then A will divide any multiple of them. So whenever of okay. So since this is named as a corollary, you should use the theorem before to prove this. Yeah. But what this say is I want you to appreciate this theorem is because, for example, like 2 divides 6 Okay, for example, and then 2 divides 8. So, okay, every time we talk about this number, right, maybe it seems abstract to you because this is all A, B, C only, okay? So whenever I talk about this A, B, C thing, right, you should have some example in your mind, okay? So for example, if I say take A, B, C from Z, so you have to go to the integer and take 3 number out, okay? And then if I say A not equal 0, then you cannot let A equal 0. So find something that's not 0, okay? Such that this condition hold. So for example, this condition hold. So the claim here is 2 will divide m plus 6, m times 6 plus n times 8, okay, for all m and n. Okay, for example, you can take minus 6 minus 1 times 6 plus, for example, 1 times 8, which is what? Which is 1 divided by 1 divided by minus 6 plus 8, which is 2, which is true, right? 2 divides 2. Okay, so whenever we talk about this theorem, you should have some example in your mind to convince yourself first. So the proof of this theorem is to apply theorem part 1 and 2. Okay. If we got time, we can come back to this proof. Oh, I leave it for your question to ask me. Okay. Next, the next one is the division algorithm. So the division algorithm, let me write down the statement first. So take A in the integer. Okay. Then we can find a unique number Q and R, okay, with the R have some restriction on it, okay, such that so we how many number we introduce? So A and then Q and then R and then D. Okay. So how these 4 number connected to each other? So such that A equals to DQ plus R. So this one this is actually quite related, quite you are quite familiar with it. For example, let's take A equals 7 and then D equals to 2. Okay. So 7 is equal to 2 times 3 plus 1. Okay. So this is our A, this is our D, and this is our R, and this is our Q. Okay. So you will notice that this number here is always less than this D here, this 2 here. Because if this is 2 or more than 2, then you can just move it across, right? So this is the remainder. Okay. The remainder is always less than the divisor. If it is more than the divisor, greater or equal to, then you can just move the extra bit into here. Okay. So why are these AD key ADQR? So there's a name for them. So A, we call it a dividend. Q is a quotient. D is the thing that divides people, so divides numbers, so it's a called divisor. Whilst R is a remainder. Okay. So quotient is like 6 over 2 equals to 3, so this thing is called quotient. Okay. So that's why the multiple, can I call it multiple? Not the multiple, the number beside the divisor multiplied 2 is called a quotient. Okay. Because quotients mean something like this. Yeah. A fraction of numbers is a quotient. Okay. And then so Q, so there's some notation for them. So Q is equal to A divided by D. Okay, so this is what I wrote here. Quotient is equal to A divided by D. Okay. If you want to see the horizontal equation here, it's like 2 equals to 2 times 2. Okay. And then R is equal to A mod D. Okay, so this one I want you to remember now because we will use it later frequently. So when I write A mod D is the remainder after you divided by D. Okay. It's A mod D is the remainder after you divide by D. Okay, so we will introduce congruence now. So the how we do how to say two numbers are congruent to each other. So take A, B in the integer, okay, and M a positive integer. So we say then A is congruent to B modulo M is congruent if M divides A minus B. Okay. This is what we did, what we mentioned in the start of the class. So we'll write A triple line B mod. So this one is called the modulus, and this one is the whole thing will be called congruence. Notice that I use a triple line here, right? This is a triple line here. Because, for example, mm, for example, let me think. So, like just now we said 13 is congruent to 1 mod of. Okay. So 13 is not equal to 1, right? Let me put 13 not equal to 1, but in the world of modulo 12, they are equal. So we use this triple line here instead of double line. So double line is reserved for number equality of numbers. Okay. Triple line is for the modular arithmetic. So they are not equal as a number, but they are equal in the world of modulo 12. Okay. So similarly, in your previously, we also have equal, right? Equal and modular. So let me bring out the issue also. So last time we talked about this one is equal as a set equality. But we use triple line for logical equivalence. Okay. So that means these two sides here are set. These two sides here are proposition. Okay. So you don't write like beside this you put two set here. Okay. Or beside equal you put two proposition here. Okay. So these are no meanings on that one. Okay. Okay. So every time I wrote this, make sure you know which world I'm living in. Okay. Equal sign for usual number, and then triple sign for modular arithmetic. Okay. So if they are not congruent to each other, then we will write A and B. So it's the negation, right? So negation of the statement. What do? We also put a slash. Also put a slash. Okay. So notice that I put a bracket here. Okay. Just now I say that okay, let's try another thing. So just now we have something like B mod M, right? Remember the remainder? So B mod M is the number that you divide by M, and then the remainder you left. Okay. So it doesn't make sense to write this, and then this. Okay. Because here is a number. Here is also a number. Okay. So number and number, we cannot really put this because it might be something, it might be, yeah. So we can't put a triple sign between number because triple sign only work for modular word. Okay. So sometime if you see that anyone write this A mod B mod M without a bracket, actually they meant this. Okay. For the congruence to make sense. Okay. So maybe I will leave out, sometime I'll leave out the bracket, but yeah. Okay. So next, theorem. So let's take A and B again. So what's the relation between the is there any relation between the congruence and the remainder? Okay, so this theorem will tell us this. So let's take two integers again, and the modulo we will leave it in positive word. So then we say that A is congruent to B mod M if and only if, okay, two direction going forward and backward. If and only if their remainder is the same mod M. Okay, notice the change of equality sign here. So here I put triple sign because we live in the world of congruence. Here I put equal because these two sides are remainder, so they are real numbers. Okay. So for example, why is this useful, right? So for example, you want to check whether 17 is congruent to 5 mod 6 or not. Okay. How do you check? How do you check? How do you check the statement here? What's the definition of congruence? Right? So if something is congruent to each other, you take the difference and then you divide it by m. Okay. So 17 divided minus 5 is 12. Does 6 divide 12? Does 6 divide 12? Yes. Yeah. So yes. Things 12 equals to 6. Okay. So 6 divide 12. But there's another way to check it. So you just compute 7 mod 6 and 5 mod 6. Okay. So 7 mod 6 is what? So 7 equals to 6, 2 times 6 plus 5. Okay. And then 5 mod 6 is 5. So both of them have the same remainder. Okay. Yeah, so what's the time? 636. Okay, I think we got time. Let's try proof one direction. Yeah. So let's do this direction to this direction. Okay. The proof I did in the class is a simple proof, so we just unravel the definition to check our understanding. Hard proof we won't do in the class to save time. Okay, so suppose we go this direction. So suppose their remainder is the same. Suppose remainder is the same. We want to show that A is congruent to B mod M. And what does this mean here? Okay, maybe let's spell out what this means. So by definition, okay, by algorithm, by what algorithm? By division algorithm. Division algorithm is actually a theorem, but we didn't prove it, so we just use it. So division algorithm says that every number can be divided. There's a unique q, and let's call it a q1, and unique remainder such that a equals to mq1 plus r1. The units, they is the unique q1 and r1 in so, okay. Similarly, we can do for b. You can divide b by m, and then there's a unit. What do you call the q again? The quotient and the remainder such that b equals to mq2 plus r2. Okay. So everything we introduce, there's a purpose behind that we need to use it afterward. So we're using division algorithm here. So actually we note that R1 is equal to R2. Why? Because R1 is the remainder A mod M. But by assumption, A mod M is equal to B mod M. Okay, maybe I wrote it vertically so that match what we did before. Over and this way. So I explained this. Okay. This one, if you really want, you can see by the way. This one. Okay. Right. So actually we have that R1 equals to R2. Okay, by this assumption here. So what we want to show, okay, we want to show A is congruent to B. So we recall the definition of the congruence mean what? We have to take A minus B and then show that it is divisible by M. Okay. That is A minus B is equal to M times some some integer. Okay. So what can we do? So now we want to compute this guy here, A minus B. Let's compute A minus B here. So then we have A minus B equals to mq1 plus r1 minus mq2 plus. Okay. So what you're left with is mq1 minus mq2 because r1, r2 is the same, so they cancel. And then you can just factorize it. So q1 minus q2 is another integer. M divides M. Okay, which is what we want. If you want to write since minus q2 is so, okay. Next, we check the remainder. So if you want to check something is congruent, you can check the remainder. Okay, and then next one is let's say they are congruent to each other again. So let's say that they are congruent to each other. So they are congruent to each other, then A congruent to B. Okay. The first thing you know is their remainder is the same. the second thing you will know is A can be expressed as B plus Km for some Kz. Okay. So this one is quite straightforward. Okay. Why? Because if you unravel the definition of this guy, okay, what's the definition of this guy? So A minus B equals to Km for some Kz. Okay, this is the definition of this, right? You take the difference and then divide it by n. Then to show this, you just move the B to the other side. And then if you have this, then you can minus B on both sides. Then you can see that n minus B is divisible by divisible by n. Sorry. Okay, which means A is congruent to B mod n. Okay. It's a good exercise. You can write down the whole statement here. So I just put the key point here. You can write down the full statement going from here to here, and then going from here back to here. Okay. Try and write it out. And then next thing we want to establish is given two congruents. Okay. So suppose you have A congruent to B mod M. Suppose M is in the real the positive integer again. So if you have two congruents, okay, what can you do? Okay, in propositional logic, we have two propositions. We take the conjunction, we take the disjunction, and then so on. And in set theory, we can take the union, we can take the intersection. So in this case, these are integers, right? Integers, what can we do? We can add them together, or we can multiply together. So the statement, the claim is, you can add the right-hand side, okay, and also you can add the left-hand side. Actually, they are congruent to each other again, mod M. Or you can multiply on the left-hand side, and then you can also multiply on the right-hand side again, and then you also get a congruence. Okay. So you can try to prove this. Okay. So why I introduce this? Okay, maybe we go to the corollary first, and then we'll talk about why we do this, all this. So the corollary. So what we all achieve now is, okay, so if you take A plus B, okay, you take the remainder, and now, so this is a remainder. We talk about equality in numbers. Actually, you can just take the remainder of A first, mod M, and then take the remainder of B, mod M, add them together, and then take the remainder again. Okay. Or if you want to compute the remainder of the product, you can do it individually first, and then multiply them, and then reduce it again. Okay. So maybe you think that, hey, this part here got more work because you want to reduce first, and then reduce individually first, and then reduce whole thing. But here you just multiply and then reduce. But if you imagine you want to multiply like 10 or 20 digit number, then the multiplication will be very take up enormous time. But if you reduce first, okay, then you can reduce the digit number and then you multiply using less time and then you can reduce again. Okay. So you also can try, if you don't want to prove, you can just read the textbook. So you can read, or you try to prove, or you read the textbook to prove. Okay. Okay. So what we have done now is we have built out a system. Okay. we build a system of Zm. Okay. So this set here contains 0 up to n minus 1. So for example, Z12, we have 0 up to 2 up to 11. Okay, so there are 0 digits here. So we build another like finite integer, whole finite integer. So how to add them here? So this is a plus with a subscript m. Tell you that this is a plus m mod m. So the plus here is the integer because everything here is an integer. So you know how to add them. And then after you add them, you take mod m. Okay. Take mod m is take the remainder left after dividing by m. Okay. And also you can define multiplication. So how do you define multiplication? You just take a multiply b and then mod m again. Okay. So this set here, why are we looking at this set here? This set here shares similar property with the integer. Okay. So for example, we have the closure. Closure. What's the closure means? So all these property we will take all the different number in the Zm. So you can imagine a Zm you like and then take three numbers. So the closure means if you add them together, okay, it is still in Zn. Still live in this set here. You can imagine, for example, in this case here, so we got, let's take 11 plus 5. Okay, this plus is the special plus, which is plus m, okay, which is equal to 11 plus 5 mod m. So notice that here got subscript m, here no subscript m, okay, because here is the usual addition. So the usual addition you can do, right? 11 plus 5, so it's 16. So 16 mod m. Hey, you see, 16 is not in the set, right? 16 is not in the set, but I take mod m. Mod m means what? 16 is equal to division algorithm. So 16 is equal to, my m is 12 in this case. So 16 is equal to 1 times 12 plus 4. So 4 is the remainder. So it's equal to 4. So when it's equal to 4, it jumps back into the set. Okay, so you always live in the set when you do the operation. So this is the closure mean. So you also can test A times B under this special operation here is also live in Z. Secondly is associative. Associativity. Associativity, I think we also encounter in the propositional logic and set theory. So what does it mean? So if you add three numbers together, it doesn't matter how you put the bracket. So that means you can do the first guy first, you can add first two first, or you can add the last two first. Okay. Similarly, for multiplication, you can multiply the first two first, and also you can multiply the last two first. So associativity. Third, commutativity. Okay, we also have encountered this before. So you can do it A plus B. Also, you can do it B plus A. Not okay. And then you also can do it A times B is equal to B times A. Okay, under this special property here. Okay. How is it? 9,255. Okay, let me talk about inverses and then we take a break. So for identity elements. So identity elements mean something that add to it, you got no effect from it. For example, if you take A plus 0, you get back A again. If you take A times 1, you get back A again. So A is called the additive identity. And then 1 is called the multiplicative identity. Okay. And then 5. Okay, 5. Let's talk about this and then we'll stop here. So 5 is the additive inverse. So additive inverse means for every A in Zm, okay, I can find a number called P first, P in Zm, such that when I add A to it, I get 0. Okay. So let's think what is the P is. Okay. You can think about it during the break or you just take a break. So after the break, we will talk about what is this P here. So there's a P such that when you add to all the number, okay, sorry. For all the number, okay, you can find a P. Give me a number, I can find one P for you, such that when I add together, I get 0. Get back the identity, additive identity. So what's this P here? Okay. Maybe I give you a clue. So in a integer, right, you just take A plus minus A, you get 0. Right? But -1 is not in this set. Like negative number is not in this set. So what do you do? Okay. So let's take a break. We will come resume at 10:05. Is it too soon? Oh yeah, 对。所以你理解那个题目，你理解那个题目。 对，它有些我分你要长大之后，这个体验可以set 的设计，最好要set，就是说这是我现在的就是发现可以让你这个是说，如果是这个主题的话，如果你是不这个就是你希望你是在你现在，如果你在应该里面，你应该应该在那个里面你的比较。因为如果你这个 source 你就是多少，我你这个我就跟我因为你讲从错跑到这个 Hey, is anyone of you come back from the visa problem? Who play you? Yang Yifang. Ah, okay, welcome back. Okay, your first time joining the physical club. Okay. Just you, another guy, Chen Jiawi. Not here. Your friend? But how do you know this machine? Oh, okay. Oh, I see. Okay, welcome back. Wonder who is Yang Po Kai? Oh, yeah, Yang Po Kai. Trying to learn all your names, but too many, 670. If we got assignment, maybe I can learn your name because I can like know you from your assignment. But don't have assignment in this class. Okay, I'll pass the anyone figure out what's the P? Uh, you want to figure out what P you can take? The P you can take. Huh? How do you know? Huh? What? Equation? Okay, so from the equation view, if you take m minus a, right? So what you do is you just add two numbers together and then you take mod m, right? So it's actually m mod m. So m is divided by m, so the remainder is zero, so it's zero. Okay. So why is it m mod a valid? Because a is always less than the divisor. So if you take the divisor minus a, so you will always uh, remain in the set of uh, Zm. Okay? Because Zm is all the number that's less than m. So if you take m and then minus all these number, you will stay in Zm again. Okay. And then the last property you share with integer is the distributivity. Distributivity we also see before, right? You n and all, and then the intersection and union. So what is the distributivity here? So if you multiply the sum, okay, and then it will equal to, you multiply each of them and add them to it. So I think, I'm not sure about you, but during my high school, we call like this, like open the bracket. But the real name is distributivity. Okay, it's the same as the open bracket. Okay. So all these you can verify that all these also shared by the usual Z. So how should I put it? Z. Okay. Z also have this property. Yes. So it's as if we are living in the world of Z, but it's a finitely many finite world of Z. Okay. Infinite is too scary, so we go to finite. Okay. Okay. Next, we talk about primes. Primes and GCD, greatest common divisor. Primes are actually the building block of numbers, integers. Is if you study chemistry before, it's like atom is a building block for the chemical element, chemicals. Okay. So primes is the building block of numbers. So what's a prime is? The prime is a number that's greater than 1. Okay. Well, in a minute, we'll talk about why 1 we don't want to consider. So a number greater than 1 is called prime if the only positive factors, again, remember factors divide the things that divides the numbers that divides are 1 and p. Okay, only 1 divided, only itself divide. Okay, only it divide itself. So for example, do you want to write example? So example, what is prime? 2 is prime. 2 is prime because 1 divide 2 and 2 divide 2 only. Okay. So similarly, like 3, 5, 7, 11, 13, 17, and then keep going. Okay, so these are prime. Okay. So these are prime. So for those that are not prime, we'll call it a composite. Okay. So uh, P in Z greater than 1, which is prime. Okay. So so for example, like 4, 4 is not a prime because what? You take the negation of the segment. So 1 divide 4, sorry, 1 divide 4, okay, 4 divide 4, and also 2 divide 4. Okay. So got extra divisor. So it's not a prime. It's a composite. So what is a composite? Composite is like mix of things, right? So 4 is a mix of what? It's 2 times 2. So 2 2's make up 4. That's a composite. Okay. In fact, in fact, by this theorem, all the number can be split into product of prime uniquely. There's only one way. But this way, of course, up to ordering because it's commutative, right? So you can switch. So up to ordering, uh, you can split every number into prime. So what's the statement here? So every integer greater than 1 can be written uniquely as a product of primes. Yeah. Up to order. No place. Of primes up to order. Okay. Yeah, just now we even talk about one is not a prime. So one is not a prime because we don't want one to be prime because only one divide itself. So only one divide it and then it divide itself. So it's the same number. So they exclude one. And then yeah, you need example for this? No need. Okay. So just take a number and then keep divided into primes. Okay, next. Next, how to test something is a prime. Okay. Usually you want to test something is a prime, you want to show that only one and the number itself divided. Right? So of course one and the number itself divided, so you need to take all the number, usually I mean, you take all the number before it and then try and divide it, right? To check whether it has non-trivial divisor or not. That's true. So, but by this theorem, you don't need to try all of them. Okay, you just need to try some of them. Okay, how many of them? Okay, let's see how many of them. So the theorem is if n is a composite integer, okay, then n has a prime divisor which is less than or equal to square root n. Okay. So to show something is a prime, you need to take the contrapositive of this statement here. So if n does not have a prime divisor that is less than or equal to square root n, then n is a prime. Okay. So you just need to check all the prime number that is less than or equal to square root n. So you are like reduce more than half of them. Okay. So let's take an example. So proof, I think we don't do in class, but this one is a proof by contradiction. If you're interested, you can go and refer the book. It's quite interesting and easy to understand, I think. So it's a proof by contradiction. So you can refer back to the book. So how to use this? So for example, show that 137 is a prime. Okay. So to show it's a prime, you just need to check whether it's divisible by all the prime that's less than square root 137. So what's square root 137? What's square root 137? Okay, never mind. I also don't know. But you can estimate it by square root 144. Yeah, square root 144 is 12. Okay. So you just need to consider all the prime that's less than 12. So for example, 11, 7, 2, 3, 5, 6, 7. Yeah. So there's only like 1, 2, 3, 4, 5, 5 of them. Okay. But but it is not divisible by all these numbers. Okay. So 137 is a prime. Okay. Okay. So the next one is more interesting. So uh, since all the number can write as a product of prime, so um, actually there are infinitely many primes. So this is called a Euclid's. Euclid is a famous mathematician in ancient time. So there are infinitely many primes. Okay. But I want to show this proof. So this proof you must see. This is a classic proof. Also proof by contradiction. Yeah. I think first two class confuses. I don't know whether you guys will confuse them. Try follow, see if you get stuck. So proof by contradiction, right? So contradiction mean what? You need to assume the negation. Right? So the negation of this statement is what? You got infinitely many, so the negation is finitely many primes. Okay? Assume you got finitely many primes. Okay, first step, say, so since there are finitely many, right? I can list all them down. So P1, P2, P3, up to some n, Pn. Okay, I can list them down finitely many. So the key is this construction here. So we look at this number here. Look at this number Q here. Okay. Q, I take it as a product of this number. Okay, plus one. Okay. Take the product and then plus one. So there are two possibilities. Whether this is a prime or whether this is not a prime. Okay. So suppose this is a prime. If Q is a prime, what happened? Then we found an extra prime. Right. But just now we only say that there's only n of them. Now you found an n plus one. Then we found an extra m plus 1, which is a contradiction. Right? Because we say only got n1, got only n of them, but found an extra one, so contradiction. So this one doesn't work. So then suppose Q is not a prime. Okay, let me add one sentence so that you don't confuse. We have two cases. Either Q is a prime, okay? So both cases you need to check. Suppose Q is not a prime. So not a prime means it is composite, right? So if it's composite, then there's a prime divisor. And then there's only n of them. Okay. So some of them divided. Okay. Let's pick one of them. Since Q is not a prime, then there's this sum Pi such that Pi divides Q. Okay. So remember the theorem we proved. So since Pi divides Q, okay, and also that's definitely Pi divide the products, right? Because Pi is one of the prime inside this product. Then the theorem is we can divide the sum of multiple of them. So Pi, in particular, Pi will divide Q minus Pi dot P2 dot P3 dot up to Pn. Okay, right? Because remember just now we proved if we divide two numbers, then we can divide the multiple of the sum of the multiple. Okay. You want me to recall them? So A divide B, A divide C implies A divide MB plus C. Or M and percent. Okay. But Q minus the product of Pi, Pj is what? Is 1. Right. So Pi divides 1. Right. Since Q minus P1 up to Pn is 1. Okay. By construction. This is what we constructed. So what number divide 1? What numbers divide 1? 1. But 1 is 1 a prime? 1 is not a prime, but we assume Pi is a prime. So contradiction again. Okay. So two contradiction. So assume that. So that's mean the original statement is the assumption is wrong. Okay. So that's mean we got infinitely many primes. You can find you can't finish finding. Okay. We're going to some infinite world now. So there's another phenomenon. So there's a phenomenon called the twin primes. So how are they a twin? Twin. So twin primes is two of them are prime, but their difference is two. So for example, 3 and 5. Okay. Next is 5 and 7. Okay. Next is 11 and 13. 17 and 19. 29 and 31. 59 and 61. 71 and 73. Okay, maybe you can keep going. So the question is, are there infinitely many twin primes? Are there infinitely many twin primes? What do you think? What do you think? What do you think? What do you think? Must be wrong. Oh, must be no. Oh, must be no. Okay. Okay. So yes or no? Yes. Okay. Some say yes, some say no. Okay. So the answer is don't know. So this one is still open. This is an open question. Okay. Maybe you can try and find. You can try and prove. If you found it, maybe you can change the world of cryptography. Yeah. Okay. Because we only relies on primes now. Yeah. Yeah. Okay. Let's think. Yeah. I think this one is BC. This one. What they did is BC. So 2000 years ago, maybe. So after 2000 years, still don't know yet. Okay. Go on again. Okay. Let's continue. Okay, we talk about primes now, and then let's talk about GCD. Okay. GCD. So let's take two number. Okay. Both not zero. So what's GCD? So you take all the divisor of A and B, okay, and then find the largest one. So GCD is the largest integer. D such that D divides A and B divides B. No worry if you don't get this line. We will get into uh, the example really soon. But I think we did this one. I remember I did this in high school. But let's see. So let's say we want to find the GCD of 8 and 64, right? So we will check what divides 8. So 1 divides 8, 2 divides 8, 4 divides 8, and 8 divides 8. How about 64? 1 divides 64, 2 divides 64, 4 divides 64, huh? 8 divides 64. Anything else? I think no more, right? Okay. I think there's more. There's more, right? But 32. 32 is quite behind, right? So you still got one more in different. 16, correct. So because these are like dual. Okay, never mind. So these are like so they are product to get 64, and then of course 64 divided 64. Okay. So the largest one is 8. Okay. Huh? Ah, okay. So yeah. Okay. So, okay. So we will denote by oh, I haven't denote, I just used it already just now. So it's called GCD already. Okay, GCD. So if GCD is 1, that means the largest common divisor is 1. So we call this relatively prime. So I don't want to write so many. So if GCD AB equals to 1, then A and B are relatively prime. Okay. So why we call them relatively prime? Primes. Prime. Okay. Because for example, GCD of who? Maybe 8 and 9 is 1. Okay. But 8 and 9 themselves are not prime. Okay, right? Because 2 divide 8, 3 divide 9. So they are not primes, but they are relatively primes. Okay. So next is maybe I don't know first. I just edit here. This condition here we will be used in next week. So since we already touched on this, so we just might as well just add this in. So we can have a bunch of integers, and then we call them a pairwise relatively prime. If you check any two of them, their GCD is 1. Check any two of them, and then see that their GCD is 1 for all of them. Okay, you need to check all of them. Okay, so this line means you need to check all of them. This one is just check any two of them, and then all of them. It's written here. This condition here is all of them and any two of them. Okay, 10:30. So, let me see if we got time or not. Maybe we got time. Okay, actually, okay, because in the previous 2 class we skipped this. So maybe let me see if we got, I think we got time. Okay, we should got time. So definition. So we got GCD. The next thing is LCM. So what's LCM? Is the least common multiple. Okay. So least common multiple of A and B is the smallest positive integer that is divisible by A and B. Okay. So for example, let's see. So okay, denoted by LCM. Okay. No worry if you don't get the definition. Let's see the example. So for example, LCM of LCM of what number you want? Pick a number. Huh? 6, 9. Okay, 6, 9. 6, 9. What's the LCM of 6 and 9? 6 and 9. What's the 6.9? Huh? 18, correct. Yeah. Okay. So if you want to do this, you just like list down the multiple If you want to systematically do it, you just list out the multiple and then find the least one. Okay. So what's the use of this LCM here? One of the uses is when you combine with GCD, okay, then if you want to compute the product of two numbers, okay, it's actually the GCD times the LCM of AB. Okay, this is always true. You can prove it. Okay, in the textbook. Okay? The product of AB is just GCD times LCM. Okay. Next. Okay, this one is really important. You must pay extra attention. Okay, this huh? This part is really important. You must pay extra attention. This is really important. It will save your life. Okay, okay. Never mind. Like Euclidean algorithm. Okay. So what's Euclidean algorithm? Okay, this algorithm is help you to find the GCD of AB. You don't need to list all the divisor down, but just use this algorithm here. So this algorithm will use the division algorithm. So let's take the statement here. So let's say you want to find GCD of AB. Okay. First of all, you need to use your division algorithm to write down what is A divided by B. Okay. I mean, just pick B as the smaller one. And then you will find ABQ. All right. So the division algorithm will guarantee you a unique Q and R. Okay. So what this GCD and B can reduce to is just reduced to finding the GCD of the divisor and the remainder again. Okay. So you can imagine you can reduce it and then you can keep doing it. Okay. For example, I will show this in an example. So for example, find the GCD 51 and okay. So first step is to use the division algorithm to find the remainder. Okay. So 51 is equal to what? 9 times what? 5 plus 6. Okay. Next, so the GCD of so now the GCD of A and B is equals to the GCD of B and R. So you need to do again. So what's the GCD of 9 and 6? So 9 is equal to 1 times 6 plus 3. Okay. So the GCD of 9 and 6 is the GCD of 6 and 3. So you can keep doing it. And then I think always you will determine it in this kind of pattern plus 0. Because this will tell you that the GCD of 6 and 3 is just 3. Okay. So in total we have hence GCD of 51 and 9 is equal to GCD of 9 and 3. Okay, so 9 and 6. Sorry, 9 and 6. So this one is by Euclidean algorithm, right? Then you keep doing again. So GCD of 6 and 3, which is GCD of 3 and 0, which is 3. Okay. Okay. So this is Euclidean algorithm. So if you want to prove this lemma here, you can check refer proof in the textbook. Okay. To prove this lemma, you just need to show that the set of common divisor here is the same as the set of common divisor here. So that when the set equal, when you take the largest number, they also will match up. Okay. And then the second Q that will save your life is extended Euclidean algorithm. After you found the GCD, right? Actually, the GCD can be expressed back using A and B. So actually, you can use A and B to find your GCD as well. So let me state the theorem. The theorem is if A and B constitute, then there's this S and T and Z such that for the GCD of AB can be written as a sum of multiple of SA. Okay, so how to do it? It's actually the backward of Euclidean algorithm. So that's correct. So let's move this here. Maybe in the textbook, right, the extended Euclidean is a bit different, not too different, but a bit stated a bit differently. But you just follow my notes here. So what I mentioned here is what the extended Euclidean algorithm. This is what I learned before. So let's use this. Okay. So we found that the GC from the Euclidean algorithm, we found that we found GCD of 51 and 9 is 3. Okay. So how to express back to 51 and 9? So you can use the backward. So 3 is equal to what? 3 is equal to 9 minus 1 times 6. Okay. And then you keep going back using the remainder. So 6 is equal to 51 minus 9.5. Okay. So which means you have minus 51 plus 6 times 9. So your S is minus 1 and P is 6. Okay. So these two techniques you have to know. We will have a lot of practice on this in the tutorial question. Okay. And then try with now there's two lemma and one theorem, one lemma and one theorem here. So we try to link this GCD back to the modular arithmetic. Okay. So what's the lemma here? So let's say if you take three numbers again, positive one, such that the GCD of A and B is 1. So that means they are relatively prime. The common divisor is only 1. And A divide BC. Okay. Then A will divide C. Okay. So that means if you have A divide BC, okay, and you know that A doesn't divide B and they don't have common divisor, then surely A will divide C. Okay. Right. So why I introduced this thing here, because this will uses the extended Euclidean algorithm. Okay. To explain this, you will use that because Because since GCD of AB is 1, okay, this means we can express by extended Euclidean algorithm, okay, we can express 1 as a sum of multiple of A and B. Right. Okay. So your goal is to show that A divides C. So C is some multiple of A, right? C is some multiple of A. So from here, maybe you can try multiply both sides with C. Okay. What do you get? We get C equals to SAC plus TBC. Okay. So you notice that here is divisible by A, right? Because you got A inside the product. Here, is it divisible by A? Huh? So TBC is divisible by A. Why? Because A divide BC, so A divide the multiple of BC. If A can, okay. So if uh, A divide both term, then A divide the sum of them, right? We prove in the very first start in the class. So hence A divide C. Okay. So we use all the tools that we have learned up to now. Okay. To see this. And then this will give a way to compute modular arithmetic. So the theorem is if AC is congruent to BC mod M, okay, if you happen to know it's a product of AC and BC, they contain the same factor, okay, and the GCD of C and M is 1, okay, C and M is the factor with the modular, then you can just cancel the C on both sides. Okay. So this is not like a let me think. This is not like integer. So integer you have like, for example, integer you very know well that, for example, let me think, 6 equals to 9. Okay. Implies implies 2 equals to 3. Right. So you can just cancel it out. Okay. But in the modular arithmetic world, you cannot just do like this. Right? You cannot just do like this. You have to measure the GCD of C and M is 1 first, then you can drop. Okay. So this proof of course, use the lemma. Or you can try it out. Or you can look at the uh, this book. Okay. Use the lemma, but not too long as well, the proof. Any questions or not? Hmm. Any question or not? Do you understand the two algorithm? Do you know how to do it? If I give you the tutorial question, you can do it. Ah, okay. Okay. No. You can try, we will try a lot of example in the tutorial. If there's no question, then maybe we'll take a break until 10:58. 啊，嗯嗯
是吗？
嗯
这个是1.5跟9，
，yeah，
然后
51跟9，
哦51跟9，哪里啊？哦这一层，这一跟9嘛，
yeah，
然后加6，
嗯，
然后你要拿的是上面我看到你要拿的是这个嘛
112跟你们，
跟6啊，这样意思吗？
是
9跟6，这个那做的
我翻了是不是？
我
翻了，什么？
可是我懂啊，这个
OK，yeah，
6跟3，
yeah，
可是这个啊，为什么它是3跟0，不可以是2跟0的？
还是跟着这个，还是你用谁来 divide 就是谁
哦，你要跟着
，yeah，跟 B， 虽然我 B 跟 Q 会反，因为就是 commit，因为他们 commit 嘛，可以反，但是主要是你要知道谁在 divide 谁，所以你刚才是拿3在 divide 嘛，怎么你又跑去2，对吧？你重点是你要知道 B 是谁，Q 是谁。
我上面这里是什么？它下面是什么意思哦？它下面就3和2来的，其实。
Yes，如果真的你要跟啊，但是问题是，如果你要，但是3乘2跟2乘3是一样，对，
因为其实如果真正它也是把0，对吧？
所以
这个1跟6也是可以变成6乘1。
你可以的吧嘞，但是你自己不要乱啊。重点是谁在底吧，谁是剩下，谁是底吧，谁是剩下的。
那这个我也是不懂，
这个懂吗？
这个我其实这个有问题，这个我根本不知道你在讲什么。
这个是我反着做吗？
你说你你你想反着做，
所以
下面往上，下面往上。
这个是下面往上，所以我现在要找3嘛，这里面哪里有3？就一个地方有3，所以你就从这里开始做，这里3等于9减这个咯，对不对？
赶过去。
对，
但如果我没有做这个之前，我是做不到这个的。
应该是做不到。
应该是做。
如果你是天才，可能可以哦。
我明显不是天才，我是天才，就是站在这里哦。哦，所以我把这个点就好。就剪了。
然后你就继续substitute 它的 remainder，所以这里的 remainder 是6嘛，所以你就可以把它的6代替掉，然后你再继续直到你停在
不长了，
对，
乘进去，然后找这了，跟这了9，
因为你是51跟9嘛，这样你就停了。
做51跟9，
你只要做回来这2个数字，你就可以停了。
9减掉51，
然
后加9减5，
对，9乘5
9乘5，哦，就是9乘5，9乘5，加45意思哦。
但是不重要啊，因为我不要把它那
这
个
9去哪里？这里减51，减51是干嘛
9加5个9嘛，所以你有几个9？
69，
一个加9，
9加5个9，6个9，这51你能拉出来。然后找到这两个关
然后就
这是它的流行性质啊。
可能啊，对
SA
，A 是
51减
1啊，
还有比较，这个是同位，
嗯
怎么办？他要我等于这样子，那这我要忘 C。
这样你就可以知道如果 C 等于什么东西哦，因为你这一个的话，你要说的 C divide AB 嘛，对不对？这样意思说你要说的 C 是 A 的 multiple，对不对？
我要说的对啊，我要说的
嗯
就是 C 等于
，Yeah，OK，
也算 AB 啦，可是为 AM
可以 AM，
啊，C 等于 AM 嘛，
嗯
就是 BC
哼，
等于
等于
AN。
对。但是所以你想从你有的东西把 C 变出来嘛？这边是 E 嘛，所以 E 的话你可以变 C 出来嘛，只要乘 C 就好。对吧？
哦，因为这个是这个来的嘛，这个来的嘛，是，
呀，
然后它有答案的嘛，它跟
对
方式呢也一样，把那个东西丢进来变成等于，
啊哈，
对吧？进来过后，我讲
对
东西出来我就从 both sides 从
对对
C，
对对对对，
很多
然后你
C 啊，
试下这个 divisible by L，如果能你就成功，不能你就要试另外一个方法，然后乘上能，然后就结束。
是，
什么意思？没有，所以你的目标是要 A 除 C 嘛，对不对？所以
嗯，
你要看一下 A 到底除不除得进这些东西嘛，对不对？
这 A 要怎样除
嗯，
？C 这里要除，它本来是我理解是它本来是 等于 SA 加
对
AB，
对
我乘 C 就变
对
成 C
对
等于
对
SAC
对
加 TBC。
对对，然后现在你 check 一下我的 A 底不底外这个东西哦。
几不几块？
对
我要除了一个，
对，你要除一次。但是我们之前不是有说过，如果他要除一个加的东西，他只要分开除的进就可以了呗。
一个加的东西，它分开除定。
对，记得吧？就最开始的时候，你看，如果你要除它加的东西啊，
嗯，
你只要分开除它，除的进就可以了。
哦，一下，
如果 A 底
A
外
OK，
啊哈
然后 C
啊
等于 A to A，这样
呀，
你就可以写成 A 除 B 加 C。
对，所以你就 check 我的 A 底外这个吗？A 底外这个吗？
现在是
嗯
A，这个一样的是吧？
嗯哼，
跟这一样的，不是？为什么会分这一？这个我懂诶，这
呀，
个就是因为它可以这样嘛，它
嗯哼
都是这个音题进来的，
嗯
所以就可以直接
嗯
B 加 C 了咯。
呀
A，
呀，
这个
嗯哼
我要弄到什么？
嗯哼，
我 A
说你要底外，你把这个整个当做一个 B，那个整个当做一个 C 嘛，
啊，
所以你要问的是 A 底外底
哦，
外，对，
所以我要问的是，要有一个东西是 C 除 B 是吗？这是 C 哦，这个当做 A，这个当做 A，
啊
这个 C 哦。
哦，没有，你看这个符号，这个是等于，这个是 divide，
哦，所以
呀，你要看的是这个东西，A divide C，所以 A divide SAC 加 T，你要看的是这个东西，
哦，
呀，
这样我要找一个 A divide B，然后要找一个
嗯
A divide C，
嗯
所以 A divide B 的时候
，A divide SAC，呀，
，A divide 这个时候，
嗯哼，
我就变成这个 MN哦，对不对？AM
可以啊
这个
，ST 是你的那个，
这个东西
嗯哼
等于
嗯哼，
AM 是，
啊，
然后这个东西等于 AM2 也可以，
然后
然后这样的话就可以哦，这个跟这个就可以加哦。
对，但是问题是这个为什么可以写成那个种方式？
这回是写成哪一个？就是我
就
讲的
为什么这个可以被 A 除？
这为什么可以被 A 除？
这个可以被 A 除比较直接嘛，因为你有 A 在里面，因为它除掉了。但是这个呢，这个你没有 A 在里面，
是哦，
呀、所以你要用 condition 哦，他告诉你哦，其实这一个可以写成 multiple，
这个可以写成。
嗯，
A B C，
呀，没有 A 可以 divide BC，
那可以 divide B C，所以这个可以
所以
啊。
这一 part 可以 divide BC，但是这个是 TBC 哦，怎么你又可以 divide TBC？
因为你讲只要
因为这个，如果你可以 divide 一个，你就可以 divide 它的 multiple，呀，所以你现在可以 divide 两边了哦，对不对？你可以 divide 两边，你就可以 divide 它的 whole，
就可以 divide 整个东西，
呀，
可以 divide 整个东西，
整个东西是 C 来的嘛，
这东西是 C 哦，
所以你就 divide C 哦，
我就一定可以 divide C 哦，因为我这里都可以 divide 掉，两个都可以 divide，我这个加前面可以 divide，这个加后面可以 divide，所以就算我加起来过后，我还是可以 divide 我们这个东西，所以 A divide C，
对，
那就做完了，
做完了。
好，这下面可以
下面这个是 extra 的东西，就是如果有两个有一个 congruence 的话，你可以把它的那个 factor 切掉，除非那个 factor 和这个 m 是 GCD，
可以把它的
是吧？
C 跟 C 切掉
对对，
，C 切掉，除非
除非
它的 GCD 里面有一个东西是
GCD of 这个切掉的东西和这个 m 是一，
直译，
你才可以切，
这个东西
啊
跟这个东西在一起，你一定要等于我才
呀，
可以切，
你才可以切，
那我们也就不能切。
不可以切，要不要试试切切看？
用这题切到，
用这题切不到，但是我就给一个 example 来切。
你切，
然后我看一下，so let's try 一下。这个好像 example 不太好，这个 example 不好，因为如果切了还是一样。我要找一个慢一点，我 tutorial 的时候找。我现在要 start quiz 先
OK，
，OK，我等下找一个 example 给你看。OK，hello, hello, hello. So I need or I split the class into 4 rows. I need the first person in the row to count how many person behind in your rows, and then come and collect the number of quiz. So I need 4 person, so one from each row. Sixteen. Just one of you. 16. 16. Wait, son, count first, count first. 11. 16. Alright. Huh? 22. 22. 16, 22, 11. And then this one, third row. Third row. How many? How many? 18. 18. Okay. So once you get the quiz, you can read it, but don't write anything first. Read it, but don't write anything first. You can read the question. By the way, close all your electronic devices, face down your screen. Okay, face down all your electronic devices, screen down. Okay, there's a correction on 2.2. So the question is not complete. Find a domain interval such that f is bijective on the corresponding range. Okay. You can read, but don't start first. You can write down your name, English name, and uni ID, student number. Don't start yet. Let everyone got the question first. And then 2.2, find a domain interval such that f is bijective on the corresponding range. Okay, 1105. So we have 15 minutes. We'll start now and stop at 1120. Let's start. Um, Hello, you need more time? Yes, I give you more, 3 more minutes. 3 more minutes. For those who have done, check your uni ID, username, English one, and then clean up your solutions. Okay, please pass your quiz sheet to the front. Pass to the front. And then the one who helped me count the number just now, please count the right number in your row. Please pass to the front. Pass to the front. Please pass to the front. Pass to the front. 11. Yeah. Pass to the front and you can start with the tutorial worksheet. Okay.
我写的很乱，我英语真的太差，写不通的。
好，我会解释。慢一点。16. 16. Yeah. And what's the third row? Third row. Third row. Okay.
拿不到啊，你去拿。
Okay. And thank you for the cooperation. I can start doing the quiz now. I mean tutorial. None. Please, sir. Hello. It's a quiz time. No, no. Huh? I think I'm wrong with the card. Oh, okay. 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 Is the question one harder or question two harder? Huh? Both? Okay. Uh, okay. Yeah, two question is like testing your whether you know a definition or not, how to check the definition, how to prove the negation of the definition. Okay. We will discuss the answer of quiz after, I think next week. Hopefully we will get it back next week. Before the exam. And also I think I plan to move the office hour during the exam week to next Thursday. I think maybe 2 to 6. I'll make announcement again. So that next week we got 2 office hour, which is on Tuesday and Thursday. Tuesday is usual 12 to 4. Then Thursday is 2 to 4, 2 to 6. So that because your guys is the last class, right? So it's Thursday, then exam on Monday is quite short. The time is quite short for revision. So you can come and find me Thursday 2 to 6. Thursday 2 to 6, you guys got class or not? SWE, no class. Okay. So yeah, the test material midterm is from chapter 1 to chapter 3, so up to next week. Okay, just now who? Jordan. Okay, Jordan asked about this theorem here. So this theorem here, right? Okay, if the GCD is not equal to 1, then this theorem here doesn't hold. Okay, I give you an example. So the example is like this. I also have AC, BC. Okay, AC, BC, you got the same factor. And then mod 4 in this case. But my GCD of the factor and the 4 is not 1, it's 2. Okay, and then this line hold, right? Because 2 is mod is congruent to 6 mod 4. 2 is congruent to 6 mod 4. Okay, because 6 mod 4 is also 2 mod 4. Right? The remainder is also 2. So they are the same. But if you straight away cancel this 2, it says that 1 is congruent to 3 mod 4, which is wrong. Right? 1 and 3 is different mod 4. Okay, so the result doesn't hold if you throw away the GCD CM. Okay, so you cannot always like see this factor is the same and just do the cancellation. No, it's not like the integer case. Okay, so let's discuss the tutorial question a bit. I'll just run through the tutorial question. Prove that 1 divides a divides 0. So just need to write a and 0 as a multiple of 1 and a as respectively. 4.1.8. This one a bit trickier. So if you divide the products, okay, and a is not 0, does a divide the factors? So the answer is no. Okay, so and then you give a counter example. 4 divides 4, but 4 doesn't divide 2, and yeah, but 4 doesn't divide 2. This one is for you to play around one. Play around with the odd number. We've touched on odd number before, right? And now we got the divisibility, so put them together and then see what we can get. Proof by contradiction. And then this one, 4.1.16, for you to practice the modular arithmetic. So you can practice how to compute mod 24, this one, for clock. And then 4.1.18 is to use the theorem we proved today to help you to compute this number. Okay, is the theorem we proved today. 4.3.2 going to the prime, so check something is a prime or not. Okay. Okay, 4.3.4 is the fundamental theorem of arithmetic, right? So you can see that in prime can only written as the prime times 1. Okay. Remember how we define primes? Only 1 and itself is the divisor. So see, only 1 itself. Okay. And these are all unique way to write. Okay, next. 4.3.14 asks you how to find something is relative, some number that's relatively prime to some other number. Okay. Find all the number that's less than 12 such that it's relatively prime to 12. So you found those with no common divisor greater than 1. 4.3.32, yeah, this is the exercise I want you to really master. So this is the Euclidean algorithm. Okay. So okay, so I think some of you like also I think Jordan just now bring it out as well. So you see I like swap the 2 and 3. Okay. It's okay you swap the Q and B, but as long as you know which one is the divisor. Okay, don't use the wrong number here. So always remember you use the divisor and the remainder. It's okay you swap Q and B, B and Q because BQ equals to QP. It's commutative in integer. But remember the command is use the divisor. Okay. The GCD is equal to the divisor and the remainder. So you keep going divisor, remainder, divisor, remainder, divisor, remainder. And don't confuse with the quotient. It's okay, you swap. Next. Okay, so this D, E, F, G, all is a practice. Okay, and then 4.3.40, you just ignore the instruction in the book. Use extended Euclidean algorithm. So I'm not sure, but some of you also confused that how do I do it? So how to do the extended Euclidean algorithm is like the backward Euclidean algorithm. What do I mean by that? I mean by because GCD is expressed as actually is the remainder, right? Okay. If you realize, if you observe, it's actually the remainder of this equation here. Okay. So how you going backward is you keep substituting back the remainder. Okay. For this case, you got 1. So 1 is the remainder, then you substitute it back the equation, and then you got 2 here, 2 is the remainder, and then you substitute the previous equation back. Okay. Maybe this one is too short. I'll show you a longer one. So this one. So let's say the GCD of 35 and 78 is 1. Then, of course, you need to perform the Euclidean algorithm first. That's why we call it extended Euclidean algorithm, right? Because you start with a Euclidean algorithm and then you extend. So you start with a Euclidean algorithm, you find the GCD, and then express this. This is actually a remainder of one equation. Okay, express it with 3 and 2. And then 2 is a remainder of another, the previous equation, and then keep going, find the remainder and then substitute back the previous equation, and then keep going until you reach the first equation, okay, where you start with 35 and 78, so that you can write as a linear combination 35 and 78. Okay, so B, yeah, similar, you see. So the GCD is the, if you notice, actually is the last remainder here. And then you just substitute back the equation for the remainder. And then you keep going up a step, going up a step, going up a step, going up a step, going up a step until you reach 21 and 55. Okay. Then you will write the GCD as a linear combination of 21 and 55. Yeah, there's a lot of practice here. I also spend a lot of time doing it. So you should try. Yeah. These numbers are not nice, I think. Because always you get 1. But 1 is also important because you know that these two numbers are relatively prime. But not nice, I mean, too long and then ugly. Yeah, ugly. Very ugly. 4.3.50, why I include this, right? Because this one is the proof of this one is close to the proof of Euclidean algorithm. They use the same principle. That means if you can show that both have the same common divisor, their GCD is the same. That's why I include this proof here. They use the similar principle as proving the Euclidean algorithm. You can try for fun, but for today, you need to know Euclidean algorithm and the standard Euclidean algorithm. Okay? Because I also know that not enough time for you guys to study all of this. Any other questions? Any other questions? Yeah. Yeah. It's Alita. See you next week. Let's stop this recording.